first continue with what I want to tell you about one example of a realization of a long-range quantum system in the lab, like my theoretician's perspective on how that is done. And we are almost done with that topic. And after that, I'll discuss a little bit what modeling or some intricacies of the use of models in long-range systems. And then we get properly, I think we start getting properly into the physics of quantum long-range systems in the second half of today's lecture. So last time or yesterday, I was telling you about this ion trap realization, and I put on the slide again, just as a reminder, some trapped ions, and with this fluorescence image here of one of such real experiments, then explaining how the ions are trapped first at distances that are quite large, so of the order of tens or hundreds of micrometers. The result of that when they are trapped, they are non-interacting. And then, but people were faced with the difficulty, but experimentalists want them to interact to get to more interesting physics, so you need to induce interactions in some kind of artificial way. The advantage of having the atoms so far apart is that there's the chance of doing something like single site control. Like you can, for example, excite a single atom by shining a laser on it, which is very hard or impossible to do in a real solid where the distances are of the order of an angstrom, like 10 to the minus 10 meters. But you can do it when the distances are of this order here. So there is the advantage of the atoms being so far apart, but then also the disadvantage that they don't interact naturally. And people came up with a, I believe, very clever scheme to make them interact. This is the calculation we went through at the beginning of at the end of last lecture, leading to this spin-type Hamiltonian that I showed you here. I was informed by one of the school participants that I messed up a minus sign in the spin polaron transformation. I didn't have the time to check it, so I'm not going to announce it, but if you redo the calculation, be warned that there might be a sign error in there. Well, where did we leave off the discussion? With this Hamiltonian there with spin-spin interactions, and I wrote down at the very end this expression here of the coupling coefficients between the spin operators at the different lattice sites. And now what the remaining thing I want to do now is to discuss a little bit how these coupling coefficients look like. And of course, in the context of the topic of my lectures, it will turn out that they lead to long-range interactions. So just as a reminder what we have in there, so these omega k are the frequencies of the phonon modes of the crystal that were excited. And in these G coefficients, I put in, well, pretty much all the other constants that occurred, which are constants from the AC Stark shift, so from the mechanism that was the physical mechanism that was used to induce this coupling, but also properties of the eigenmodes of these oscillations came into there. This is when Fourier transforming the expressions as I mentioned in the derivation. So yeah, so it's what we have in there is phonon frequencies and properties of the eigenmodes as well, and physical constants of the constants of AC Stark effect. These three elements are all in there. And now evaluating these expressions explicitly is quite a task, and what was really done in the context of these experiments is that the phonon modes and so on for these lattice geometries that you see there were calculated for the lattice sites that are used or that occur in these experiments, and the resulting plots are shown here. So what you see on this axis is the spin separation, so this is distance. The claim is that it's going to be a long-range interaction, so we want to see a power law on the distance. This is why this is a logarithmic scale here, and the interaction strength here is plotted. The one obtained here with this formula is obtained here also on a logarithmic scale. And now this is done for experimental parameters that are used to excite these phonons. And at this point, the story gets a bit, I would say, experimentally oriented. So in principle, people can build experiments, usually very small and in 1D, where you can excite whatever phonon modes you want in whatever combination with whatever amplitudes that you like. This is an amazing property, and this has been experimentally shown for one-dimensional ion chains of the size of the order of 10, with extreme experimental accuracy, where this can be used to have, you wish your couplings between site 2 and 7 and between 3 and 8 and in whatever combination. And if you have enough lasers, which means one laser per coupling, pretty much, you can do this. So everything is possible. Realistically, in the penning trap experiment that I showed you, there is a one parameter family of couplings that can be induced by changing the angle of some in-shining lasers that are used to excite these modes. And what happens then is, with changing this angle of laser light that is shown onto shined or shown. No, I'm not quite. That is incident on this crystal. You end up with either one of these curves here. So for one kind of parameter value, you get an interaction that is essentially not decaying with distance. And so this is alpha equals 0 if you want. And so the fit here gave 0.01, and and then changing the experimental parameter, one can in these calculations get to alpha 2.72, and at least theoretically one can changing one experimental parameter, the whole range of values of this long-range exponent alpha can be varied between 0 and 3. And this, for the study of long-range systems, is an amazing capability, at least in principle, because in all other platforms that people are considering, there may be long-range interactions, but the exponent is fixed. And therefore, you may study properties of this long-range type of interaction, but it's very hard to study the dependence of the long-rangeness of this parameter alpha. And this can be done here in this case of these ion trap experiments. In reality, there are experimental constraints so that in this experiment, for example, they don't really get much larger than 1 with the exponent. So these are theoretical results, but these values are close to 2 or even close to 3 have not been reached in that particular experiment. But with changes to the experiment, this should be possible in principle. And of course, you see, as always, this is not perfect power laws, but there are some deviations, especially for larger distances. But at larger distances, in the experimental photo that I showed you in this fluorescence image, there were also boundary effects where the lattice gets a little bit distorted because the trapping potential is not flat, but it's slightly curved at the boundaries, so there will always be these boundary effects. But overall, I think this power law decay is reasonably convincing, and which is why in this Hamiltonian the this couplings ij are at least modeled or considered as proportional to 1 over I minus j to the power alpha. So the power law long-range interactions with alpha in the range between 0 and 3, at least theoretically, with experimental constraints. Yes. Sorry, say it again.
So what happens if we use the frequency 1 gigahertz? So if we increase the frequency, we get this larger alpha. So why alpha equals 3 is the upper limit?
Yes. So there's frequency here. If I now out of my comfort zone, if I remember correctly, frequency here is frequency of the modes that are excited, and you don't have whatever you want available as phonon modes in the crystal. So it's about it's not the frequency of the in-shining laser, because if I remember correctly, it was the angle at which the laser was incident that affected which of those modes are then excited. So I'm a bit vague here now, because this is like stuff that I learned at some point when I spend a week in the lab, but it's not that this is really my expertise. But there is a boundary that you don't have the capabilities to go beyond this value of alpha 3.
Okay.
Yeah. This is these colorful diagrams are just illustrations of visualizations of long-range interactions. So if in this here, for example, alpha equals 0, this is just if you take alpha equals 0 on this lattice that kind of resembles the experimental one, then all the connections between all the spins are present, and in the color coding here, they're all of order 1, so they're all strong. This is what this image says. And if you go to alpha equals 3, which is on that side here, then the nearest neighbor interactions are of order 1, so they are red, and the next nearest neighbor interactions are of order whatever in colored in that way. So you're with alpha equals 3, you're already at least approaching something like nearest neighbor is by far the strongest interactions, and the others are quite a bit weaker. This is just an illustration of this fact. Yeah, sure.
Yeah. So like all of these curves, you see there is a small region and there is a gap, there is a large. So what is? Do you know the reason for that?
This I don't know. So I see you mean this gap here at this point, yeah.
All of the point there is a gap.
Yeah. I don't know. Sorry. Yeah.
A is the alpha you are referring to again.
So sorry. Yes.
And this alpha is the slope of this curve.
Yes, exactly. Like in a logarithmic plot, doubly logarithmic plot, it's the slope, yeah.
What would happen if we go to slightly lower frequency? I mean, I'm just wondering whether alpha negative is also experimentally possible.
No, again, I think these frequencies shown there are not the experimental control parameters, but I think they are the frequencies of the phonons that are excited. And
there's nothing smaller than 100.
I think I believe that this is the frequency of the lowest phonon mode is this drumhead mode where everything is oscillating like this, and this should be the frequency in this setting associated with this frequency.
Is alpha negative even possible?
Good. This is an interesting question. I mean, possible. As a theorist, I can say I write it down and then I have it. But so alpha negative would correspond to interactions getting stronger and stronger the larger the distances, and this resembles confinement in QCD, where I believe that at long distances it should be linear, so it would be alpha minus 1. if that whole discussion would hold up with someone working in QCD and if it would make sense to consider it in this context. Look, I've like vaguely considered this question and considered looking into it, but I've never seen anyone really going into this direction or trying to connect it in some way also with QCD in some way. But maybe it's something interesting to do there. I don't know. I've never seen any work where, at least in the spirit of as I said, long range you can mean anything what you want it to mean, but I have never seen these types of questions being asked in that context. Anyone of the others working in the field? No? Yeah.
But it is experimentally really hard, it will be really hard to achieve like alpha
Yeah, certainly. So unless you say you want to study QCD where you may have it for free, I would believe it's very hard. Look, as I tried to point out in the historical overview yesterday, that I mean, long-range systems had been studied already for 1 or 2 decades before I would claim a proper experimental realization came up. So yeah, sometimes it takes time, and also time to search for the right platform where this may be possible. But I wouldn't know, I don't see these types of platforms doing it at the moment, at least, yeah. This is maybe a good point for the transition to the next slide. So this is what just the flavor of these ion trap experiments that I wanted to give you. And before moving on to a different topic, I have one more slide about other types of platforms of what I call synthetic quantum systems with long-range interactions. And this is certainly not complete. It's a selective choice of those that I came across, and I maybe sometimes was a little bit involved in some projects there. And the first 2 that I have on here, polar atoms or molecules and Rydberg dressed atoms. This is, in this case, neutral atoms that get somehow trapped with usually laser fields in that case. And so certain types of atoms, for example, have a large dipole moment, and when you trap these atoms, you may try to use this large dipole moment as interactions that extend far enough so that you have atom-atom interactions. This was a very challenging thing to do for people, because you may have dominant shorter range interactions that are also present that you kind of have to suppress to get into the regime where these long range interactions with exponents usually of going like 1 over distance to the power of 3 are the dominant contribution and are not, say, orders of magnitude smaller than nearest neighbor interactions, and therefore you would not see anything of these long-range interactions on the timescales that are available experimentally. But there are experiments being done, especially these Rydberg dressed atoms, so atoms that are excited to very high principal quantum numbers, usually between 50 and 100, so that the atoms take on extensions of many angstroms. So they can be very, very large, extending over quite large portions of the system, and have large induced dipole moments in that way, with interactions depending on some experimental choices that are either 1 over 3 r to the 3 or 1 over r to the 6. Yeah, these laser-driven atomic clouds, I think I'm gonna skip this one, but I wanted to say a few words about cavity QED that is shown here. And this is a platform, I believe you will learn more about it next week when Prof. Gosh, I think is the name, he might be...
He cancelled, he cannot come.
He cannot come.
So maybe whatever you want to say.
Well, I'll just say a few sentences so that I don't have, I won't go through a detailed discussion of this, but I want to point out that there are some very similar ideas to what I told you about the ion traps. So, and the similar idea is, so cavity QED means the cavity is an optical cavity. So think of like two mirrors, and you have light in there bouncing back and forth or forming standing waves. Usually there's also some leakage out of this cavity. And then what people do is they have a cavity where there's usually one light mode that is occupied in there, and they also can trap atoms inside that optical cavity. Now, what is happening that similar to the ion crystals, these atoms there will naturally, if you want, form a kind of crystal, a lattice, and in that case, it is because of the optical modes in there, like the nodes of the standing light wave that is essentially in there will create maxima and minima in which these atoms then are located, so that a lattice is formed. And then in the spirit, similar to what I explained for the ion crystals, there are extended modes, in this case the same optical modes that are trapping the atoms, that will also mediate interactions between the atoms. So the spirit of the whole thing, you have extended modes, and you use these modes to induce interactions between the atoms, and because the modes are extended, the interactions are long range. This spirit is the same in these cavity QXD experiments than it is in the ion traps. The difference is because of the uniformity of these modes in here, that the exponent you get is always alpha equals 0, so it will always be infinitely extended interactions. Always meaning, to my knowledge so far in all experiments, but I talked to some people from the ETH Zurich, where one of the most successful experiments of this type has been conducted in different variants over the past 10 years, and they have ideas how to go to at least slightly larger exponents alpha, so go away from alpha equals 0, but to my knowledge it has not been done in that platform. I think this is what I wanted to tell you about platforms. Now, pretty much independently of the platform, just a few sentences as an overview now that say in the trapped ion crystals that I told you a little bit more about, what can people then do in an experiment? And of course, as always, capabilities are large, but they are not unlimited, and it really depends on every specific platform, what can people do. So if you want to observe some kind of physics, so the first question is preparation of initial states. There's, in these experiments, for example, fully spin polarized states, like all spins up, is something that usually can be done very easily in these experiments. Something with a spatial pattern, very often like spin up here and spin down there, or is usually also possible. In some of these experiments, there's single site control. You can say all spins up, initial state, one spin down, and then see what happens. This already gets more tricky. There you need single site control, which in these 2D ion crystals has not been achieved fully, but people are on the way, whereas in the 1D ion traps, which are much smaller with only usually 20 or so ions, this can be done very well. So it really, there's different capabilities depending on the platforms. Entangled initial states require a lot more work, but have also been like something like a GHZ state, like a superposition of all up and all down state. There's also schemes to implement this. Then after implementing an initial state, it's running the dynamics. So then people do quench experiments quite frequently. So you prepare some initial state corresponding to some Hamiltonian, like the fully polarized state, for example, and then let it evolve with a with a Hamiltonian of which the initial state is not an eigenstate to have interesting dynamics, and also ramp experiment where a change in the Hamiltonian is implemented slowly, like by slowly changing the magnetic field, usually have all been realized in ion trap experiments, for example. Yes, please.
So in cavity QED case, when the exponent is 0,
Yeah.
it's kind of like, do we see some extra features which are not visible when, say, the exponent is 3 or 6? Like some extra phase transition or something?
Yes. And this will be the topic of the next chapter, pretty much. So we get to that either at the end of today's lecture or tomorrow. Yeah.
One question, so in this ion trap that what we were discussing, so what is the, like, of the order of how many ions can we trap and make the crystal?
Yeah, you really have to say in which platform, in which lab, in which city in the world. So the one that I showed you with this 2D crystal, this is, I believe, still the largest. So this was a breakthrough in the terms of number of ions they had in there. This is paper, it's already 10 years or so ago. They had 300 something, but this is the lab where I spent like a week or so to learn a bit the details about the experiment. They also, at the time already, could do more than 1,000, but with the trade-off that control, in some sense, got a bit less accurate. I mean, there's so much fine print to that. For example, in this penning trap 2D, I didn't mention that so much, but the disadvantage you have is because it's a static magnetic field, you can imagine what it will do to your crystal. If the magnetic field direction is that one, and here you have the crystal, the whole thing will be rotating. So you always have to work with a fast rotating crystal, which makes, this is why single site control is so much harder. So it comes with difficulties, but you can make larger systems. And if you're interested in collective observables and you don't need single site control, then it's a great platform. In 1D ion chains, it's a different kind of trap. It's a power trap that uses oscillating fields. There, the experiments got stuck at roughly 20 ions for quite a while, and a huge also financial effort by some guy, Chris Monroe in Maryland, pushed that to 50 now. But this is like, apparently it increased the cost of the experiment by an order of magnitude as well. So apparently it was a big deal to do this. And it's not that it scales easily. So it's not that you put in a little bit of more money and then you get to 100 or so. And of course, the field always has as a benchmark value the quantum advantage. So can you do something that you cannot easily do classically? And the usual number of for spin systems where you can diagonalize and calculate whatever you want on a classical computer is 20 or 30 or something like this. And therefore, with the ion trap size of 20, people were unhappy because they never could claim the quantum advantage, whereas with these penning experiments, you can. Yeah, there's other types of experiments with neutral atoms where thousands of atoms can be much more easily done, and these experiments seem to scale better. There's again lots of fine print to that, yeah.
Because then they don't have to worry about this rotating.
Yeah, so this is specific, but even for the rotating ones, they are now working towards single site control, and so it seems to be possible to do it. I mean, when exciting or reading out, you kind of have to follow the crystal. The frequency is, I think, 10 kilohertz or something, so it's not slow, but apparently they're getting there, so yeah. All right. The last comment on what people then do in experiments. So question is, after some dynamics, what can you read out? So the easiest is usually global observables, like, say, a magnetization of a spin system. Reading out in this fluorescence plot, it would be only atoms in, say, the spin up state would be fluorescent, the others not. So you take an actual photo of this and you look at it and you can see how many of the photons are in the spin up or in the spin down state. And the photo is really unique. You need a microscope, but you photograph through a microscope, and then this is what you see, because the distances are so large, as I told you, 10 micrometers or so. You can even see with the bare eye the ion cloud when it's fluorescing, but you cannot distinguish all the details of it. So you see a little speck of light where the fluorescence is coming from, and they tell you these are the ions in the trap then. Correlation functions can also be measured. This is a bit more complicated. I won't go into the details here. And of course, more involved protocols, not in ion traps, I believe, but for measuring entropies, for example. There was a big deal when measurement schemes for measuring something like an entropy were also possible. But this is roughly what we have in these platforms. Good. Are there more questions related to the experimental setup? Yes, please.
Sorry if you mentioned this before. Compared to the amplitude of the interaction, what are the time scales over which the experiments are compared? So you have these interactions, you have mentioned the scaling of the interaction, but there's an amplitude.
Yeah.
So relative to that, how long does the experiment reliably last?
I remember calculating this when working with the experimental guys in something like milliseconds, and I believe it was in the milliseconds regime. But the important question, so I will need to look it up. The important question is always not what is the time scale, but what is the time scale compared to the time scale on which before external effects set in, before you have decoherence of your system because of external effects which at some point happen. And the important observation is that the time scale of decoherence was, I believe, more than 2 orders of magnitudes larger than that induced by the spin interaction, which means you can do a lot of interesting physics, but of course you will not be able to observe proper thermalization of a crystal itself. But I have the actual numbers because I had to compute them when working with experimentalists, so I can look them up afterwards.
One more question. By tuning the photon excitations, is it possible to selectively couple, let's say, 10 times the 4th cubic?
Yes, this I believe I mentioned briefly. It is possible in principle when you say you have all experimental capabilities, and in this linear ion trap experiment for a very short chain of, I believe, something like 10 atoms, the group of Chris Monroe in Maryland as well implemented this to say they can do like a programmable ion trap computer. If you want, you tell them which of the 2 atoms you want interact at which strength, and you choose this for all pairs of atoms, and they can do it. But they need, I think it was 1 or 2 lasers per pair of atoms to have the laser with the right frequency for doing that, and which is an insane. So it scales badly with a number of lasers involved, and therefore is not very practical. Yeah.
Like it's not a fraction or something, like close to 3. Like how do you get this?
I think they're given by the type of physical interaction that you're having. For example, the first 2, it's dipoles interacting with each other, where you get this 1 over r to the 3. I mean, this is just from the physics of interactions of dipoles. There is an angular dependence, of course, as usual with dipoles. There's a cosine of the angles between them, which I didn't put here, and it depends on the geometric arrangements whether it plays a role or not. And in the cavity QED, it's by the homogeneity of the cavity mode that is sitting in there. So the cavity is constructed such that you have plane waves standing in there, And means they are spread out over the whole system in that way. This is the reason. Yeah, so I think there's the physical mechanisms that are used for in these others have these fixed numbers in that case, yeah. But I mean, if you would have asked me before, do the phonons lead to different exponents? I guess I wouldn't have guessed it. So I don't think to me it wouldn't have been obvious in advance. Different phonons will lead to a power law, different power laws. So. Okay, then I'll move on to the next part, if you're all happy with that. Good. So, as I said, the plan for now is that I move away from the experiments and come to, before I come to the proper physics effects of long-range systems, so the question we had from the back before, so do we see differences at alpha equals 3 and alpha equals 0 and so on? The answer is yes. So there are differences between long and short range. This is really what this is going to be about, and we are getting there shortly. Before that, when we do theoretical physics, we need good models, and we need to understand what the models tell us about the physical systems that we're interested in. And I'll just introduce the two models that I'll mostly use in the rest of the lectures over the days. You have seen it's Ising type spin models is one of them, so you've seen it before, but I want to make a few comments on that will be important later on. So let's get into that. No. So that should be chapter 4, models of long-range systems. And the idea here, of course, will not be to describe a certain experiment as precisely as possible. So this is not what the modeling is about, but the whole physical section of my lectures will be about minimal models. What is the easiest to solve model that I can find that is complex enough to show a certain type of effect that can occur in long-range systems? So it will all be about simple models, and I'll have models where, depending on the choice of parameters, I can make them even simpler, and I'll use these choices whenever possible to get to calculations that can be done on the blackboard. So we'll be looking at lattice models, as I mentioned yesterday already before, and usually it will be in 1D, but I'll make occasionally comments about generalizations to higher dimensions. All the calculations I'm going to do actually in the following lectures will be in 1D, which doesn't, and sometimes the results extend to higher dimensions and sometimes they don't. And the first class models or class of models will be long-range quantum spin chains, not only the Ising chain, but mostly long-range quantum spin systems. Spin, as I also mentioned before, does not refer to a physical spin necessarily. It only means that the Hilbert space associated to any site is a complex vector space, and for spin 1/2 that I'll be exclusively using, it's going to be C2. So this is just what the Hilbert space of one site is, and then I'll have many of those. So everything that happens on such a Hilbert space as a complex vector space, I'll call a spin chain here, and the working horse here is the transverse field Ising model, which you have seen before, but I write it down for a reason here. We need a bit of space in here, so if you, when you take notes, make sure you leave it. I'll come back to that in a second. All right, this is the model. We had it on here before. J is the magnitude of the spin-spin coupling. H is a magnetic field. This here, the spin operators, the Pauli spin operators is the X component. The coupling I put into the Z component. And because X and Z, because of that choice here, this gives the name transverse, of course, to that Ising model. In some later chapter, I'll also use a longitudinal field. Longitudinal meaning, in contrast, of course, that I put a Z here so that the field part is in the same direction as the interaction part. Well, what are other relevant aspects? Boundary conditions. There's a lot to say about boundary conditions, especially in the case of long-range interacting systems, because I'll not make it a main topic here, but the longer the interactions are, the less relevant the boundary conditions are. Of course, we were familiar with the fact that if you have a short-range interacting system, and when you make the system large enough, at some point, pretty much all boundary effects, not quite all of them maybe, but they will become irrelevant because they are they are of order 1 compared to bulk properties that are of order n, and therefore you can, in most cases, neglect them. Boundary conditions, if you have a long-range chain and you say the boundaries, you use periodic boundary conditions, there's of course, the effect may not be of order 1 because you have many interaction bonds that cross the boundary. So depending on closed or open boundary conditions, the effect can be of order, well, n in the case of infinite range interactions if you cut all the interactions at this boundary. So boundary effects are not necessarily irrelevant, but my take here will be mostly that, again, I want to get to simple models to show the effects I'm interested in, and for analytic calculations at least, it will be mostly periodic boundary conditions. As soon as we have periodic boundary conditions and translation invariants, just for that simple fact of translation invariance, calculations become much simpler. It may very well be worthwhile to investigate open boundary conditions, but then analytically this already becomes either unfeasible or a lot harder already. So that's not such an easy thing to do. Yeah, then the main question about models here will be, or I choose them for them to be solvable, which is an interesting concept. I mean, what does it mean that a model is solvable at all? Depending on the field and the context, this can mean many different things, from you have an exact analytic closed expression for something, to there exists an algorithm that scales polynomially in the system size that can solve the problem numerically. This is sometimes also considered as a solvable model. So there is a whole range, and there's no clear notion of what it means for a model to be solvable. But so I usually mean here that at least I can boil it down to a reasonable calculation, like diagonalizing a matrix of size n. And if I do this, then if I only have to do this, then this is considered solvable. You have to compare this to what Leah mentioned in her talk, that a whole spin chain problem scales exponentially with the system size. And if you boil it down to diagonalizing a matrix of size n, then you can be kind of happy. But in most examples I'll show you, it will be deriving exact solutions that you can write down. So.
Does solvability means integrable?
Yes and no. No. So sometimes you have a chance of, so in many cases the model will also be integrable, but there are cases where you can, where you get to a model there where you can, for example, you cannot analytically compute certain quantities that, like spectral properties or so on, that you would be able for integrable system, but there's certain things you can still do for that model, like compute the time evolution for a specific initial state, or calculate or show the existence of a phase transition. And so I mean, it's really here in the vague sense, we can do something analytically. In most cases, as you will see, the model will be not integrable, for example, but look, this model, for example, will not be integrable. The nearest neighbor version is, and the infinite range version is. And I will show an exact calculation for the infinite range model, which is integrable. But we have results that I'm going to point you to that are for the alpha, for like small but finite alpha, like not zero, and where the same kind of results hold. So in this sense, whatever I really write on the board will mostly be for integral models, but I'll discuss what is done for non-integrable models. And sometimes there are analytic results of some sort even for the non-integrable cases, like existence of a phase transition, exactness of mean field. These are things we will come to. Yeah, just as a reminder for you, what is solvable? So the nearest neighbor version of this model, of this transverse field easing model, is solvable. This is an integral model. How many of you have seen this, like solving the transverse field easing model? Is that kind of like a good fraction of the people here? This is a very interesting thing, which, because it's nearest neighbor, so it's so short range, I can't do it in a long range lecture, but it's standard textbook material. You'll find it easily in a very didactic way, and the buzzword here is a Jordan-Wigner transformation. And this is a transformation that maps spins onto fermionic operators. And the mapping you can always do, but in many cases it doesn't give you beautiful results. So you can do it also, you can do the mapping for the long-range easing chain, but it does not give you a simple model. But if you do the mapping, which you can look up easily in textbooks of this Jordan-Wigner transformation, so the mapping is obviously not that one. You just don't replace spins by fermions. So this is maybe misleading, but it's a mapping of the spin component, say spin Z, is mapped onto some function of creation and annihilation operators that are fermionic. That is what is really going on here. And the interesting thing is that if you do this mapping for the transverse field easing chain for which it was designed, kind of, then you get a simple model that is quadratic in the fermions. And because it's quadratic in the fermionic operators, you can then solve that fermionic model. then the other interesting case is alpha equals 0. This was mentioned before, that it makes things a lot simpler, and the reason is that the system then will have full permutation symmetry. All sides interact with each other in the same way, so you can in principle commute them, permute them, and you get the same. And this higher symmetry also will lead to methods to solve this, and then which will be discuss this in more detail, that for alpha smaller than the dimension of the system, and at the same time, and also system size going to infinity, then the properties of these alphas smaller than d will in some sense be equal to, well, some properties of the system will be equal to those of the system with alpha equals 0. So in this situation, it is very similar to alpha 0, and this is also something that can be exploited very well. Now, why did I choose this model as one of the class of models that I want to look into? So I want the model to be simple and solvable, but of course I could do it a lot simpler than that. So I also have some expectations what I want the model to show, and this is some interesting physics. And in the context of this model, it will mostly be related to phase transitions, which I'll abbreviate with PT, and quantum phase transitions. So the important point here is that this model has such, well, depending on parameters and things, will have, well, for sure these, and sometimes these. With phase transitions without the Q for quantum, I mean phase transitions occurring at finite temperatures and quantum phase transitions occurring at 0 temperatures. So I'm sure you know about phase transitions. Is quantum phase transitions a topic that you've come across? Yeah, looks like, yeah, to the large part, yes. Is that a question, or was that, like, it was just a, okay, thank you, yeah. So this is the reason why we don't choose an even simpler model than that. And as a reminder, to compare with what we will have later on, I'll remind you of the properties of the nearest neighbor version. Of this transverse field Ising model, properties in relation to these phase transitions. This will of course be important because the content of the later lectures will be in what sense long range becomes different or richer than the short range version. So this is what we want to compare to. And the nearest neighbor transverse field Ising model has a quantum phase transition, and it does not have a thermal phase transition at a finite temperature. This is maybe not so unexpected because it's, well, most one-dimensional systems don't have a thermal phase transitions. This is not a 100% strict statement. You can get around this. And you will see long-range interactions are one way of getting around this statement. So, but the nearest neighbor version, this is the case. And last reminder will be the phase diagram of the quantum phase transition. So the quantum phase transition of that model happens at 0 temperature. So temperature is not a parameter, but the magnetic field in here is. And as independent of this field, there will be quantum phase transitions at the values -1 and 1, if I didn't mess up the constants here, but I think it should be all right. And the phase transitions happening here is that, so forget about this axis at the moment, that for field values that are small, like between -1 and 1, the field term is not dominating, but the interaction term is dominating. And what this interaction term does, it tries to align ferromagnetically the spins in Z direction. So you will have a in Z-oriented ferromagnetic phase. So this is what happens in this region here. And outside, this is, I mean, I'm not going to discuss this here in detail now, but the field will dominate, and the sometimes it's called paramagnetic phase, sometimes the name field polarized phase is given, because the field will just be so strong that it will orient the spins dominantly in the x direction, and this is the other phase that is happening here. And what is looked at 0 temperature is, of course, the ground state, and the ground state will change at this point and at that point in some non-analytic fashion and in the infinite system limit, and this is what this quantum phase transition is about. So now I have this other axis here, and this will be my alpha, and so I will tell you that what happens that, so then of course the nearest neighbor will be somewhere high up there, and we have alpha 0 down here. So what I told you just now, for the nearest neighbor model, the phase transition happens at -1 and 1. So, but making alpha smaller, this value will change in some way, and there's no exact result known for that, but this has been computed then by approximate methods, and it's the critical field at which the quantum phase transition happens gets larger with decreasing alpha.
This is 1 with j equal to 1, otherwise it is equal to plus j minus j.
Yes, absolutely, you're right. Or I divide by j here, which is also the...
So that line is like if I have particular value of alpha, at which each value I have a transition. Those lines are...
So no, these lines now are the... Before I was discussing only alpha infinity, like nearest neighbor, and now I say if I do a plot as a function of alpha, then nearest neighbor, so the value at which the transition occurs is 1. So this is, I'm going here. But when I change alpha, I will go slowly away from 1 and go down here. Yes, yes. Yeah, and this one as well, yeah. And so there's a reason why I stopped here at some point, but this is, I'll get to this discussion just now. All right, this was just a quick reminder, and now I sit before that up there. Now I have to, do I have colors? That would be amazing. Oh. So if you look up the literature on long-range systems, then you may in many cases find that when the exponent alpha becomes smaller than the lattice dimension, that people will put in some prefactor here. I'll generally call it n. So this is a normalization factor that depends on the system size n. And for example, in the case of alpha equals 0, like mean field interactions, people write a prefactor 1 over the system size, 1 over n in here. And this is an interesting concept, and I believe it has led to a lot of confusion in the field of long-range interactions. So because it's not always done in the same way, and I believe that some people, even a few people working in the field, are not quite aware why they are doing this and why they're allowed to do this especially. So I want to spend a little bit of time discussing this point. I think it's a very interesting one. You had a question.
For alpha equal
I can't discuss this now before I have discussed the point that I started discussing now, because it will depend on this. So, right. So what is this prefactor all about, and why have people introduced this prefactor? So in general, I mean, if I tell you this is my model, how can I just tamper with it? How can I just fiddle around with it and say, oh, I want the interactions to scale with the system size? I mean, maybe physics has given me a type of model, and when I do gravitational systems where people also do this, I mean, gravity, the interaction of gravity does not depend on system size, so nature does not provide this feature, right? If I have two particles interacting by gravity and I'm adding a third one, the interaction between these two does not get weaker. It just remains the same. But so there is a lot of, I think it's interesting and sometimes confusing what is happening there, and this I want to discuss with you. This is actually, I know I'm talking about long-range quantum systems. This point is not quantum specific. You will also, you might also see this again in maybe Alessandro's Campus talk and so on. But I think it's important to explain this now. So this is what I'm going to try now. Good. So now I got the wrong. There am I. Good. So how does the usual argument for introducing this factor go? It has to do with the concept of extensivity. When is a quantity extensive? When it scales proportional to system size in the large system limit. So the typical, scales linearly with n for large n. And this concept is very common in statistical physics and thermodynamics, and the usual quantities. So energy, for example, is said to be extensive in the sense that it scales with system size, and the intensive energy here, this then is supposed to be a quantity of order 1, so does not change significantly with system size, and this is the scaling behavior. Idea is just you have a block of some material at some temperature and another block of the same material at the same temperature. You put them together, and the temperature is an intensive quantity. It will be unchanged. The energy of the composite system will be doubled. I mean, that's just that. And for the entropy, similarly, the entropy is then an extensive quantity, and again with this guy here, the small s being a quantity of order 1. And the very relevant concept in statistical physics and thermodynamics, I'll get a little bit to that, and it's well known in statistical physics, and I'll argue that this is because statistical physics is so dominated by short-range interactions. So let's just use our model and ask the question, is the long-range transverse field Ising model extensive? So what we need to do is try to estimate the size of these terms. So this is what we're going to do now. And let's start with the easier one, with this one here. Sum of I from 1 to n of sigma I x, and just look at the absolute value of this. Well, we do the sum and put the absolute value here. This is 1, and because the sum has n terms, then this we get n here, so this term is extensive, as simple as that. the more interesting one is the interaction term. So we look at some ij from 1 to n, sigma iz, sigma jz divided by I minus j to the power alpha. And we do the same kind of steps like bounding by putting the absolute value in here. These here have absolute value 1, so we end up with a double sum I j from 1 to n I minus j to the power of minus alpha, if I write it that way. Then with the next step, let me first write it down, but this, what I wrote down here, it's a little bit depends in the details on the choice of boundary conditions and the notion of distance that one is then correspondingly using, but the differences are so small that then are going to go away in the large n limit anyway. So you can convince yourself that this here bounds that side as well. And now what we can do for this sum here is do an integral approximation, which I can construct as an upper bound. And I'll write down in a second what I'm doing. Let me first write down the result. Integral from 1 to n over 2 dr r to the minus alpha. It's really, if you take this sum here, it's really super easy. You say, I can say, well, j, and this size here, or the term in the sum will be, well, something like this. Will be the points where I have values that I'm summing, and well, I can do something like a Riemann construction, and I say, well, this term, this is the one here I take separately, and the other boxes here I'm bounding by the integral of this function here, which is what I've written down here, and that's the estimation. And the result is of this here is, well, asymptotically for large n, dropping many, n to the 2 minus alpha for alpha smaller than 1, and n for alpha larger than 1. And well, I can do the equal sign wherever I want because it's going to be equivalent anyway. So for alpha larger than 1, this term is extensive. For alpha smaller than 1, it is not. And this is the reason where if I want to make this term extensive, I have to introduce a term here that is scaling with a system size for alpha smaller than 1 and is not scaling with a system size for alpha larger than 1. And you can easily do the generalization of this calculation to higher dimensions. It's not super complicated, and I just tell you what the result is. So you will get an alpha over d here, and you will have validity of this term for alpha smaller than d and alpha larger than d. Right, so the long-range transverse field Ising model is not extensive, or the energy is not extensive for small alpha, smaller than the dimension. And if we want our Hamiltonian to be extensive, we therefore have to introduce a term that makes it extensive, if we dare to do so. So let's write down what the term would be. So I will now as a notation, I will use H tilde if I introduce that factor here, and I'll use H if I don't, so that we can distinguish the two Hamiltonians, because now for explaining what is happening with this rescaling, I want to compare these two Hamiltonians, obviously. And then from this result, I can easily read off what then the definition of this n of n must be. And it's going to be n to the alpha over d minus 1 for alpha smaller than d. It's going to be 1 for alpha larger than d. And I mean, you can, of course, also do the integral for alpha equals d. And then you get a logarithmic scaling, so it's ln n to the power of minus 1. As a clarification, of course, here I showed non-extensivity by terms of a bound, but then you can ask, well, is this bound really satisfied, or did I do my bounding just not well enough, and maybe it does not really scale that way? But it's not that hard, especially in that model, but also in other cases, to construct either a lower bound, or what is easier, just to come up with a counterexample where you see that this term here will become large. Like in this interaction term, if I say I consider the state where all the spins are pointing up, then I immediately find that this state will have that scaling, and therefore the bound cannot be smaller than this n scaling that I derived here. You have a question?
Yeah, so I understand the extensivity argument, but I was wondering whether it's also related to the fact that if you do not put on that normalization constant, it might so happen that your ground state is not bounded anymore. So that does not imply any physically meaningful Hamiltonian.
Sorry, say it again. So if you do not put on the scaling,
Yeah, your ground state will scale, I think, it will go to infinity as you take n to infinity. And usually ground state is supposed to be extensive, to be lower bound.
So you're saying I should not only, no, but isn't that because by looking at the absolute values of these sums, that I get both of them? Yes.
I'm just saying that I think that's also a point, right? Because for physically meaningful Hamiltonians, we know that the spectrum has to be lower bound.
Yes, I'm sure at least you need this for many cases. Do you? I mean, so yes, you're right. You also avoid this problem if it's going to minus infinity, which is also why this absolute value is there. If we would in which case we would run into this difficulty, I don't. Would you see a problem, a kind of system where this would occur, or is that just a general thought? Or
I think it's general.
Yeah. Okay.
Why is there an ln for alpha equals to 1 or d?
Sorry.
Why is there ln for alpha equals to 1? Scaling there Wilson goes at n for alpha equals to
Well, if alpha equals d and I integrate, so if here I integrate over 1 over r in one dimension.
there is an n outside, then that will be the bigger term than ln n.
But this n, yeah. So in here I didn't write down. So here, if I would write down the alpha equal d result, I would have it in here. But I want the prefactor such that it is extensive. So I want to have the n, and this is why. Okay.
So because just coming back to his question, so for classical long-range systems, you invoke extensivity because, okay, ultimately you want to have phase transitions and you want two terms in the free energy.
But I'm getting to that, yeah.
But for quantum systems, let's see if I want to, okay, so classical system, the argument is that you have a free energy in which you want a competition between the energy and the entropy contribution, and if you don't have it, then you cannot have phase transition. So therefore, I better scale the energy.
Yeah.
But suppose I want to study phase transition at 0 temperature, so then there is no entropy contribution. Then free energy is just the energy. So then that same argument doesn't work. That I want.
Yes.
So then probably this one is it suffices to say that I want to have a ground state whose energy is bounded from below, and therefore.
But you would have in this case as well, right?
No, I'm saying like which of the two arguments should one invoke for?
Look, I will invoke other arguments in the following. So the one that you're mentioning with the free energy, I'm going to present in a second. But there's also, you can ask about timescales on which interesting dynamics happens. And it will be a similar argument that you would then have in a quantum system. Yeah. Right, so now we know what we need to do to make the interactions extensive, and then I think two questions remain. Do we want to do it, and are we allowed to do it? And I think that's both interesting questions. So, first one. Are we allowed to rescale interactions? And so on physical grounds, if you have a certain system that you want to study, like gravity as it's given to us, in principle, you cannot just change something in the Hamiltonian as you wish, even though you may want it to be in some way. I mean, that's not good enough a reason, but there is something, I'll just like vaguely call it mathematical equivalence here, equivalence of the rescaled and the scaled model, which is a reason that allows us to do it in at least most cases. So let's now say we keep at n smaller than infinity. So we stay at finite systems for the moment. And if we do that, then what I can do, say that what I'm really interested in is, say, the partition function of the real Hamiltonian, like the not rescaled one, the one without a tilde, and which is a function of beta and h. And this is, of course, as you know, the trace of e to the minus beta h, which I call this now h of the field h. This is the same Hamiltonian as here, but I want to have this field now as a functional dependence here. And now what I can simply do by saying, if I want this to be equal to some other trace that I'm going to write here, e to the minus beta, but I want now to use the tilde Hamiltonian, and I want this side to be equal to that one, I can say, well, I look at this Hamiltonian at a rescaled value of the field. And I scale, and then I still have to divide again by n of n, the whole expression here. And if I do that, then this here will be the partition function with respect to the tilde Hamiltonian at the inverse temperature divided by nn, and the field being multiplied by nn. And this is just a super simple example to say, if I do this rescaling with that prefactor, as long as I stay at finite systems, I can always do this because I recover the result that I'm really interested in, and I know its functional relation to what I may have computed. And then this is for all kinds of equilibrium physics that you're doing. And you can do, so let's say this is example 1. Example 2, you can do exactly the same thing. I'm not going to write it out in detail for the time evolution of a state, time evolved with respect to the Hamiltonian without a tilde, and you do the similar one-line argument, and you say this is equal to the time evolved Hamiltonian with respect to the tilde Hamiltonian with the rescaled field h times nn, but this happened at a rescaled time t divided by nn. So, yes.
So when you write this Hamiltonian, you only multiply the scaling with the first term, but
Yeah.
here you are multiplying both the terms.
Well, so here in the Hamiltonian, I rescale only the first term, not the field term, because this is extensive anyway, so I would only have to fiddle with that one. But now I'm asking the question: if I have done the rescaling and I have calculated my partition function, and then I say, but now gravity does not have that rescaling, and I want to know what the real gravitational potential has as a partition function, I can say with this rescaling relation, I can relate the result that I have to the one that I may want to compute, which is gravity without that rescaling. And then I say, this is what I mean with this equivalence. If I have computed this, but the relation between what I want to compute is simple enough that I can recover the result that I may want in any case. Yeah, because otherwise, if you work in real gravity, you may have to justify why this now should people find this interesting if gravity does not have this rescaling here. Yeah.
The intuitive idea behind this, just to generalize the concept of this coordination number that we have in like when we have nearest neighbors, we just multiply with some.
Yeah.
And we do some multiply with the factor, which is the coordination number.
Yeah. So I think what you're suggesting is to say that this is like going to a higher dimension, or this is like going to a higher dimension.
No, because since alpha is so in case of nearest neighbor, we have all the interactions are equivalent.
Yeah.
But if we have long range interactions, in some sense we have to account for the fact that when we go like towards next nearest neighbors or higher neighbors, like next to next neighbors, there should be some way for the coordination number to also change in some sense. Like this probably accounts for that factor. It's not really the particles interacting fully. It's exactly the same as the nearest neighbor or to the next nearest neighbor. And
Yeah, I mean, so usually coordination number would be number of nearest neighbors, and now you're saying I'm connecting also to the larger ones, but I don't count them fully because they have a certain weight. Yes, I believe you can see it that way. And what I was just guessing that you meant, there's another way of seeing that is that going to larger alpha in the same spirit of coordination number corresponds to going to higher dimensions effectively, which, I mean, higher dimensions have higher coordination numbers, and in that spirit you could also say making alpha small, you are connected to more, which is similar to what you have in a very high dimensional lattice, so that there are also some similarities to dimensionality of the lattice going to infinity. So time's always running up. Question part 2. Should we rescale interactions? So for finite systems, as I was trying to argue, I mean, I can do it, I cannot do the rescaling, whatever I want, it does not make much of a difference. Whatever feels better, but the moment I want to invoke a thermodynamic limit, it does make a difference. Well, this doesn't, I mean, it still has happened to me that I had a numerics paper with system sizes of the order 20 or 30 for a long-range system, where then the referee said I have to introduce that that scaling factor. Otherwise, it's not a good long-range model. So I don't remember whether I followed his request or not, but it did not make sense to me. Anyway, so should we introduce this factor? So if we want to do thermodynamics, then say the canonical free energy as a function of beta and h would be an important concept. I give this an index h to say for now I'm using the Hamiltonian without the tilde. And well, as you know, this would be minus 1 over n beta, and I'm going to use the infinite system limit, so I put a limit n to infinity here. And then the logarithm of the partition function, so of trace e to the minus beta h. And now I'm going to make the argument that Shamik was mentioning briefly before, that this here will be, because of the non-extensivity of the Hamiltonian in here, you have the e to something that is overextensive. You take a logarithm of it, you'll get something that has a prefactor that is not cancelled by this 1 over n, so this will not be sufficient, and therefore for alpha smaller than 1 or smaller equals than 1, then this here will be infinity. Because a 1 over n is not enough to cancel the n that gets with exponential and logarithm that I'll get out here. You can recover this in detail if at the same time, if I would do the rescaled Hamiltonian, then I'll find something that is finite. Now the last point I want to make, so we still at the moment, well, for finite systems we don't have a good reason here. Maybe something may become infinite that we don't want to be infinite, but there is a more interesting and relevant point that I want to make. Instead of rescaling the Hamiltonian here, we could also say, well, why not just fiddle with this definition here of the free energy and put an independent factor in here, which I could easily do. So I introduce a factor, well, let's give this one a little inverse hat just because I'm running out of symbols otherwise. So I define a new free energy now, which is very similar to the one that I had before. And I now, as I mentioned before, I put this other factor in here. So I change the n dependence. So for example, for alpha equals 0, I will put this will be a 1 over n squared factor here. And this will be enough to make the free energy finite. So now the rest of this formula here continues like up here. So this is the same thing. But so I think it's pretty clear that this will make it finite. I'll still write it out to show you one last interesting point before I think we get to the end. So trace e to the, and now I write down the terms of the Hamiltonian here, beta j, sum I j to n. Well, let's put our little model in here. Plus beta h, and then the sum over I and sigma ix. This should be the expression for the free energy with that rescaling in here. But now if in the same way I'm trying to pull that factor in here, or I'm looking at what remains of that here in the thermodynamic limit, it's not too hard to figure out that now with that prefactor, I will kill everything that this term will contribute. Because this now is scaling like with n in such a way that in the large n limit, it will always be dominant compared to this term. So this here will be minus so same expression, but without that term. So it will be this will all be the same, and this here will be gone. So this is my schematic way of saying same and gone. And the result is, what we get is the free energy function, this funny one with a hat here, at the temperature beta and at no magnetic field or any magnetic field. So it will lose, I will lose the field dependence here. And now if you say, this is the argument that Shamik was making before, if I say the interesting physics of this model that I want to study, as I told you before, has to do with the magnetic field, that has to do with the phase transition. I want a balance between the interaction term and the field term, and the competition between the two is giving me the quantum phase transition. And it's also relevant for a balance for a thermal phase transition between the interaction term and an entropic term. And I will not have any of this if I don't use this rescaling here before. I'll lose the field dependence in that case, and I lose other properties depending on what quantities I'm considering. So the point is here, I might fiddle with the free energy function, but it's not a good, so this F tilde is not a good idea, because the most interesting physics is lost. Well, interesting is of course always a subjective thing, but I would claim that this is the most interesting part here. So there may be a good reason to introduce that factor, and now, as you've seen, I've of course chosen this factor. It's for a certain purpose. Like the purpose here is for equilibrium statistical physics in this example, where I otherwise get either ill-defined or boring quantities. I introduce the factor such that I have interesting physics in there. And then the meaning is of course that the thermodynamic limit is always an idealization. So I'm not really what I really want to know is where's the transition for a very, very large but finite system, and I use the thermodynamic limit as an idealization. So it doesn't make sense to say, well, if I don't do the rescaling, I don't get a phase transition because it falls out in that way, but well, then be it that way. That's not the physics I'm interested in. In the very large finite system, I may have to go to very, very large values of the field to see it in a system of 10 to the 20 particles, but there will be a field value for which this transition will then still occur. And this is a bit the spirit of doing this. So it is justified to do this, to introduce this factor, and it has a meaning, and you can relate your results to the original unscaled Hamiltonian in some way, and therefore it is a useful concept for studying. Without this concept, there will be a lot of models will lose interest in their long-range version, and with that factor they'll keep it, and but in the following, we will sometimes have this factor, and for other problems we won't have it, because it won't be relevant for everything. We may look at dynamical properties of systems without using that factor, and it may still give us interesting physics. So it's not needed for everything, and we will use it when we need it and understand what it means and how we can get back to the original Hamiltonian from the results that we have and translate them. This will be the spirit of it. All right, then it's time to finish. I'm a bit over time, sorry. And if you have questions, either now or later over the afternoon break.
Yes, there are no further questions, so we can thank Mikhail.
Thank you.